One small step for man, a giant leap for mankind. These words, spoken by the astronaut Neil Armstrong, mark the day when humans first set foot on the moon. Stepping out of our planet has opened a whole new chapter for humanity, and we haven't looked back since. Space exploration has brought us so many advancements in science and technology that we would not have imagined otherwise. Today, I would like to talk about a potential breakthrough in space travel, that is, electric propulsion. Unlike the conventional chemical thrusters used in propulsion, electrical thrusters use electricity to propel an aircraft. Even though this technology might appear to be very modern or straight out of a sci-fi movie, this technology was actually first thought of way back in the 20th century. For an object to move in space, we need to do either of the two things. First, either we need to apply an external force, or the object needs to lose some mass in the opposite direction of the desired direction of movement. Electric propulsion uses the latter principle. It uses the principle of conservation of momentum that was given by none other than Sir Isaac Newton. The propellant used in such thrusters are noble gases like xenon and argon, which can attain very high exhaust speeds of up to 5,000 meters per second. However, because gases are very light, the thrust that we attain in this type of systems is between 0.01 and zero point 0.5 newtons. Now, this force might appear to be very insignificant, which it is, but one thing that we need to keep in mind is that these propulsion systems can be kept on for months at a time. So they give us high efficiency, providing persistence rather than the brute and unguided force that chemical propulsion systems provide us. Now let's get to know some electric propulsion systems. The first one is the gridded ion thruster. As the name suggests, this type of thruster uses a set of two grids made up of molybdenum to accelerate the ions of an ionized gas. First, the neutral gas is bombarded with highly excited electrons to ionize it. Then, these ions are shot out of the grids by applying some potential difference between the two plates uh, so that we get some reaction force which helps us to move the spacecraft forward. As you can see in the figure, there is an electron gun present on the left side, which provides the gas with highly excited electrons. So these electrons then ionize the gas present in this area of the thruster, and the positive ions that we get are then further accelerated by these grids present on the right side. One grid has positive charge and the other has negative charge. So this creates an electric field which accelerates the ions. Also, you might notice that there is a neutralizing electron gun on the top right corner. So this gun it provides electrons to the ions that have left the thrusters. This is done to neutralize these ions so that they do not return back to the thrusters or they do not react with the surroundings. To calculate the thrust in such an ion thruster, this equation can be used. Here, J with subscript B is the beam current, V sub S is the beam supply power voltage, V sub G is the coupling voltage between the neutralizer and the facility ground, M is the mass of the gas ion used, E is the charge of electrons, and alpha and F are constants. Graded ion thrusters were used in missions like NASA's Dawn mission. Now, as I had mentioned earlier, that graded ion thrusters are very efficient systems. The Dawn mission had reached up to a speed of 11 kilometers per second and had traveled for around 1.5 astronomical units, which roughly translates to 220 million kilometers. Next, we have another type of electric thruster, which is called the Hall effect thruster. Hall effect thrusters accelerate a plasma jet using a radial magnetic field and an axial electric field. These two fields are placed perpendicular to each other. Uh, Now, unlike the gridded ion thrusters that we saw, These thrusters do not, the Hall effect thrusters do not use highly excited electrons to ionize the gases. Instead, they use anodes to ionize the gas. Also, these thrusters do not have grids to accelerate the ions. So after this gas is ionized, the ions are then accelerated using electric field, and they leave the thruster, providing us with some useful thrust. This was all about the electric field. However, magnetic field has a very interesting application in this machine. So as we know that when electrons they move through a magnetic field where the lines are perpendicular to the direction of motion, these electrons they start revolving around the magnetic lines. This is exactly what happens here. So when the ions leave the thrusters, the electrons try to move in the opposite direction towards the anodes, but they are trapped by the radial magnetic field into revolving orbits. So the electrons they are prevented from reaching the anode. And about the ions, they are not affected by the electric field because their mass is much heavier than the electrons. So they pass through the thruster undeflected. As you can see in the figure, there are two magnetic coils present. One is the inner magnetic coil and the other one is the outer magnetic coil. These two coils are opposite in poles, so the electric field, so the magnetic field is radial throughout the chamber. The second thing we see is the anode or the gas distributor. This anode is the one responsible for giving us ions of the gas, and the ions are then pushed through using electric field. Uh, One thing to observe here is that there is a cathode neutralizer at the top right, just like we had in graded ion thrusters. So this does the same job of delivering electrons to these ions so that they neutralize. The radius of the circular paths of electrons is known as the Larmor radius, which can be calculated easily by using this simple equation. Here Ri stands for the radius, m is the mass of electrons, E is the charge of electron, B is the magnetic field, and V is the velocity of electron before it got trapped into the magnetic field. Hall thrusters are used to maintain satellites into their geostationary orbits by doing north-south or east-west corrections. Hall thruster is now recognized as one of the most interesting concepts uh, because of its performance, mainly in propellant mass. It saves about 400 kilograms of payload for a 40 class satellite in a mission of 15 years. The final thruster that we are going to look at is called the Vasimer engine. The Vasimer engine stands for Variable Specific Impulse Magnetoplasma Rocket. This type of thruster uses plasma jets to propel. An electric power source is then used to ionize fuel into plasma. This electric field heats and accelerates the plasma, while the magnetic field acts as a steering wheel. It directs the plasma into the proper direction before it is ejected from the engine, thus giving us thrust. The Vasimer engine can also control the amount of thrust produced so that it can increase or decrease the acceleration. It even features an afterburn mode which allows it to sacrifice fuel efficiency for additional speed. It is like a turbo mode for the Vasimer engine. The possible fuels that we can use in this engine may be hydrogen, helium, or deuterium. The use of hydrogen as the fuel comes with its own side benefits. Hydrogen absorbs radiation, which acts as a shield for the spacecraft. So it can protect the spacecraft from the harmful radiation while acting as the fuel at the same time. Also, hydrogen is abundantly available in the universe. So the spacecraft would only need a fuel that would be enough for one way, as it can refill at the destination for its journey back home. This engine also does not use electrodes for plasma production or for the plasma's acceleration. Hence, its lifetime is also not affected, is not limited to the corrosion of the cathode or the anode. Hence, its lifetime is a lot longer than the conventional electrostatic propulsion systems. The Vasimer engine is still in its inceptive stage. Uh, as of August 2017, it has only been fired for a total of 10 hours. At its full theoretical potential, the Vasimer engine would be able to carry humans to Mars in only 40 days. However, before this is made possible, the Vasimer engine it needs uh, to make many optimizations and undergo many breakthroughs before its full potential can be harnessed. In conclusion, electric propulsion has many advantages over chemical propulsion, mainly in the way it uses its energy quite efficiently. However, we still have to depend on chemical propulsion for leaving the Earth's gravity before we can come into space and use the chemical propulsion. uh, Years and years of research into the aerospace field has brought us to this point where we can use the energy from sun using solar panels to power these spacecrafts that are operated by the ion propulsion for virtually indefinitely. Uh, Electric propulsion, along with many other breakthroughs that we are having right now, truly make this time the golden era of space exploration. Thank you.